Okay, so we have an example that should show some of the workings of work. And it's a pretty straightforward problem, but I think it's gonna help us suss out some of the details. So the question is, what is the net work done on this object that I've drawn right here? Okay, and given in this problem are three forces, and we're given their magnitudes here. And we're also told that this object is moving to the right 3 meters while these forces are being applied. And the question is, all right, what is the addition of all of those works, right? Sort of like the net force is the vector sum of all the forces. Well, the net work is going to be the sum of all the works. The nice thing about net work, though, is that it is, remember, work is a scalar. So we're just doing arithmetic once we know the individual works done by F1 and F2 and F3. All right, so let's go ahead and apply our equation for work to all of these things, because if we're looking here, we have both forces and displacements for all three forces acting on this object. And we're told what the magnitudes of all of those displacements and forces are. So it should be a pretty straightforward thing to just write down what the works are. So here we go. Work 1 is going to be F1 times D times the cosine of the angle between those two vectors. And if we're looking up here, well, we see F1 right here, and we're moving to the left. And so the angle between those two things is 0 degrees. So this just goes to positive 1, and we're left to just multiply 5 newtons by 3 meters to give us 15 joules of work. Positive work, so that force, because it's acting in the direction of the displacement of the object, would tend to add to the amount of energy that that object has if it were the only force doing work on this thing. Now, of course, the amount of work being transferred, or rather, the amount of energy being transferred to or away from the object, so the amount of work done on the object, depends on the other forces, too. And we can already see that W2, so the work done by force 2, right here, is potentially going to be something that changes our calculation in terms of the amount of net work, because at least a piece of that force acts in opposition to the direction of its movement. So let's take a look at it. We've got F2, we know its magnitude. We, of course, are going through the same displacement, so that's well known. And the cosine of, okay, well, it's 60 degrees between the horizontal axis and where this thing is pointed to, so that right there. But we want to measure the angle between F and D, and so we're going to get cosine of 120 degrees, right? So that's the one little wiggle that you might get caught by if you tried doing this problem and weren't thinking really carefully about what that theta in the work is equal to FD cosine theta equation is, right? That's the angle between those force and displacement vectors, not the angle measured from the positive x-axis like it often has been in the past. All right. So once we plug all of this in, cosine of 120 degrees gives you a negative 0.5. F2 is 9 newtons in magnitude, same 3 meters, negative 0.5, and that gives us negative 13.5 joules. Okay, and the component of F that we are looking at, so this one sort of right here, the part that's along the axis of the displacement, though in this case opposing it. It opposes that displacement, and so we would expect it to slow this thing down if it was the only force acting, okay? And lastly, we've got W3, and we can write out the equation for this just for completeness sake, but the cosine of what angle? Well, it's the angle between D and F3 is this one right here, so this is going to be 90 degrees. This whole thing then cancels to 0. Okay, 0 joules of work done. And to calculate the net work done, Well, we can just add all of these numbers up. Well, we end up subtracting, but it's the arithmetic sum of all of these things, which gives us that 1.5 joules of energy is being transferred to the object, because this is a positive number. Okay, and there's our answer. Now, there's a couple other ways you could do this, right? If you were so inclined, you could find the net force first. You could find the net force first, right? Do our usual sort of sum of vectors using these magnitudes and the indicated directions in the diagram. Find F net, which is equal to, I've been using this notation, but they mean the same thing. And then you could find the net work by saying, okay, well, if ft cosine theta is the case, then we just do this and do it out. If you do that, try it. And if you do that, though, you come out to exactly the same number if you've done everything correctly. All right, and this one, I would argue, is quite a bit simpler if you just go force by force. Now, sometimes that's hard to do. You might not know what all of the forces acting on an object are. Might not have all of their magnitudes. They might be difficult to estimate. They might be varying over time, all of that kind of stuff. And so working with works, these scalar quantities, can be helpful. And so we're going to take a look at some other situations where we might not know certain things and be able to work our way around to the appropriate answer using this new technique, okay? But the first thing we're going to do after we do this example, which we have done, we're going to connect kinetic energy, this new quantity that I've mentioned a couple of times now, to work and vice versa. So I'll see you for that one.